Hello everyone, I'm Manaswini Konna and my topic today is about sound classification using deep learning. The contents I'm going to discuss are listed here. Abstract. Coming to abstract, sound classification is one of the most widely used applications in audio deep learning. We usually do the sound classification using deep learning, which is very famous and also which is a very good method to classify the sounds. In this project, I have taken the environmental sounds and classified them into their categories. So for that, I have considered a data set which consists of around some 8,000 sounds, 8,000 different sounds. This involves learning to classify sounds and to predict the category of that sound. Audio classification, the very first step we do is the audio classification. For this we need a data set. So I've considered a data set which is the urban sound 8K file data set, which contains about some 8,732 audio files, in which it includes 10 different types of sounds like dog bark, drilling, and sirens, and also the children playing, etc. So in this project, we go with a step-by-step process in which the first step is we download a dataset and then convert them into the spectrograms and then input the spectrogram images to the CNN file, which later divides them, process them into a source, which can be inputted into the linear classifier, which divides the sounds into the subcategories. So the next step here is the data set consists of two parts of audio files, like which is one is the metadata and the other one is the audio files. Metadata is a combination of, like, it consists of the audio files, the file names, the sampling rate, and also the length of the file. Audio files is just the audio file. Metadata also contains the .wav files. So here is an example of the sample drill, which is recorded of around 4 seconds of length. This is a picture of the drill which is recorded for 4 seconds. The flow chart for the project is, as I said, we first download the data set. The data set I've considered here is the Urban 8K sound set, and then prepare the training data. We prepare the data to train the model. So we prepare the training data from the data which we have downloaded, and next we pre-process the data for training. We again pre-process it for the training, and then we build the model using the pre-processed data. Then after building the model, we train the model, and then we go for the inference. So these are the steps that are included in preparing the training data. We usually, as I said, we have the audio files and metadata. We have two kinds in it. So the metadata contains information about each audio file. So it is the metadata as a CSV file. We can use pandas to read it. Pandas can be imported in Jupyter Notebook or in whichever platform you run the Python. We can prepare the feature and label data from the metadata. For example, if we don't have a metadata, we just have the audio files, then we can scan the audio file directly to prepare the training data. So if we just have the audio files, we need to take the .wav files and then by scanning the directory and then list all the audio files from the directory. Then we prepare the file names for the audio files, and also we do prepare the class names, and then the class names are later converted to the class IDs. So like if we take a graph, we can take the file names in the x-axis and we can go with the class IDs on the y-axis. So we are after the in the process of pre-processing the training data, so we transform the prepared file names in the x and the class IDs in the y. We then transform that. So for that, we will load the audio from the .wav files which were extracted before, and then we like if we consider some of the audio files, some audio files have are double and some are single, like they have two sets. two sets of audio files. So in order to process the data, we need everything in the same format. Like we don't want some in the monochrome and some in the stereotype. So we convert everything into the stereotype. If they are in the monotype, we create a duplicate of the file and then convert them into the stereotype so that every data is in the same format. And then we resize to fix the length. We check the length of every audio file and then resize them. Like if the length is big, we cut it to 4 seconds. Like for all the files, I have taken a limit of 4 seconds, so I set all the audio files to the 4 seconds length. And the next step is audio augmentation time shift, in which we augment the audio. We check the time shifts of the audio and we augment it. So we just want everything to be in the same format, like same length, same data, and same kind of processing. Next, we convert to the MEL spectrogram. We take the audio and we convert it to the MEL spectrogram. MEL spectrogram usually takes the audio and convert the .wav file into the images. So that later that can be used to differentiate the audio files. After converting them using the MEL spectrogram, we take, as I said, the MEL spectrogram, it is MEL frequency substrate coefficients, which is a very better version of the spectrograms we use. It also collects the audio in the form how the humans hear it, how clearly we can hear it. We can get the output index so clear way we use the MEL spectrograms. And then the final step in the pre-process training is the spectrogram augmentation. In this, we use the frequency masking and time masking to set the audio files. So frequency masking is we cut down the frequencies by using the horizontal bars in the spectrograms. And also the time masking is we cut down the time by using the vertical bars in the spectrogram. After this, we get data which is very everything is similar. Like you have the similar length, similar time shift. So in that way, we can process everything in a good way. So this is the thing I have explained you. And the next step is building the model. After pre-processing the training data, we need to create a model and build it. So we built a model. The data pre-processing steps that we just did are the most unique aspects of our audio classification problem. So we built a CNN classification architecture to process the spectrogram images. The CNN architecture, it takes a batch of pre-processed data and then it goes through the four CNN convolutional layers, which creates them creates a clear flattened prints of the images, which are then passed through the linear classifier, and then the linear classifier divides the sounds into their differences. So like if you have car horn, dog barking, and drill, the linear classifier differentiates them into each part. So next we need to train the model. We define the functions for the optimizer, loss, and scheduler to dynamically vary our learning rate as training progress, which usually allows training to converge in fewer epochs. If we consider like as we downloaded a dataset, we divide the data into 80:20 ratio, in which the 80% is for training the data and 20% is for validation. So 80% of the data we have converted, we use that to train the model. Like we train the model, like we can divide the dog barking sounds and we train the model. In that way, the model can identify which is similar to the dog barking, and then it identifies that this is dog barking, this is drilling, and this is the car horn. We keep track of a simple accuracy metric which measures the percentage of correct predictions. Inference. As part of the training loop, we would also evaluate our metrics on the validation data. We run an inference loop taking care to disable the gradient updates. The forward pass is executed with the model to get predictions. So whereas coming to the conclusion, and I hope all the project you have understood in, the classification of sounds is useful in every aspect, like to divide the kinds of music and also to separate the sounds in investigation, like when they have the music talking and also the sounds of gunshots, they can separate it using the deep learning, which is very helpful. We have now seen an example of sound categorization from starting to the ending, which is one of the most fundamental challenges in audio deep learning. Not only it is useful in a variety of situations, but many of the principles and approaches we have discussed here are also applicable to more complex audio issues like automated speech recognition, in which we start with real voice, comprehend what people are saying, and convert it to the text.